So hopefully you all can see my screen as well.
Yes.
Okay.
Yes.
Well, thank you, Priscilla, and thank you, the IEEE Society for the opportunity to speak tonight, and mentioned my Stanford affiliation, ASIA, where I spend most of my time these days. Also, a little thanks to FiTunes, one of the companies. You'll see a slide or two from them, and some from ASIA, some from Stanford. And I'd really like to give special thanks to Yun Liao, who's a PhD student at Stanford, who's been working with me on some of the aspects of this as well. So we're going to talk about, it's kind of tongue in cheek here, it spells out the word air, but artificially intelligent regulation. So I hope to give you some fun thoughts here tonight about that, looking at maybe where we might go in particularly wireless communications here over the next decade or so. So with that as maybe a beginning, let me just pull up a slide here and ask you, we tend to have machine learning, robots increasingly important these days, maybe robots for everything. So the first question is, would you let a robot lawyer defend you? Would that be good? It might be, especially if it's something really important to you, like if you've done something bad criminally, would you trust that? Would you allow that to happen? I'm not sure what that blue line, I don't know if everybody else is seeing that also, but something came on there. Hopefully that goes away. Or maybe even more intense, would you let a robot doctor take care of you? I hear obviously remote medicine heading that direction. So robots doing that. What about us engineers? Will we get replaced by a robot as well, right? So that's a possibility. But here, suppose regulation, and here I'm thinking communications regulators, became increasingly machine-driven or artificially intelligent, or a robot, if you will. So that's maybe the thought behind this. And in particular, some of you may recognize this is a photo. It's a few years old. This one is the FCC commissioners, and there's actually two. The present chairman and the former chairman are on the ends there, but this goes back a few years. But suppose the chairman themselves were a robot, all right? So we call that the artificially intelligent regulator, or AIR. What would that take if we did that? And would things improve? How much improvement would be possible in wireless communications if we did that? And if you're a regulator and you're watching this talk, I've given it once before. I'd probably give it a few more times in various places. We're not talking about kicking them out of their jobs, but we're just looking into the future and saying, okay, suppose the regulatory policy and so forth became increasingly artificial intelligent. What could we do with that? So, I think there's some fun topics that occur, and there will be some challenges, but just maybe this might occur. So there are evolving connectivity trends and needs that I'd like to talk about first, just kind of set the stage for this, maybe some common terminology. Looking at, I think many people are familiar with the Cisco internet report that they update every so often, and one of the things they try to do is count the number of different types of devices, obviously getting into tens of billions for Internet of Things, expected to grow and explode really more so in the future. And there are a variety of different reasons for that: sensors, obviously cameras or other things, thermostats, so forth. Information sharing for computing or other purposes, entertainment purposes, augmented reality, virtual reality, driving up bandwidths, transportation, of course, smart cities, Industry 4.0. And let's think about that, all these things connecting, obviously, and how many hotspots are there for Wi-Fi worldwide? Well, here's the numbers that I found on the internet there from the Consumer electronics reference shown, and it does seem to, it's a very large number, over 500 million, but it does seem to be kind of slowing down in terms of the number of hotspots that get out there. And if you were to ask the question about cell towers, how many of those are there? It's not nearly as many as the Wi-Fi hotspots, of course, but there's about 4 million of these globally that exist. So looking at that, there's probably a lot more things and communicating devices than there are access points or cell towers. And let's just say, well, maybe the number of cell sites and Wi-Fi access points might go up to be as large as 1 billion. But suppose we had 50 billion things. So that's maybe 50 devices per access point or radio node, if you will. But if that number of devices, you see some people talking about, exploding with clothing and everything that we do and touch, having sensors in them eventually, maybe there's 1 trillion devices, not 100 billion or so as projected. And you can have as many as 1,000 devices per node. And the reason I look at this ratio is because some things start to change when the number of communicating things or devices starts to exceed some basic parameters that we have in communication design. And I'm going to explore that here in the talk today. So let me pursue on. In addition, of course, there's the bandwidth content. Obviously, virtual reality, augmented reality are notorious drivers of bandwidth. They're not in such a heavy use perhaps yet today, but we're seeing more of this. Can be caused by entertainment needs, but also could be for people working at home, in particular blue collar types of activities in the future, increasingly robotic but controlled remotely. Needs for bandwidth maybe in the enterprise area also increasing into that range of even a few hundred megabits per second to gigabits per second for individual types of uses and applications with these things on the horizon. And then some of the needs for this important also is the actual latency. And so if we have lots and lots of things and we're scheduling them in time, of course, that creates a delay issue in communications. So, and what kinds of latencies are tolerable? Well, 5G communications advertises today an edge, a latency from the edge of the network to the end devices of 1 millisecond or less. From the clouds, maybe tens of milliseconds, public clouds. Perhaps as opposed to private clouds, another factor or 2 or so on top of that. So we have potentially many communicating devices, and as they become more video or presence-based, bandwidths increasing as well. So we see potential for a lot of devices per node, and then I'd like to kind of do another thing is kind of go back in time here a little bit and just talk about the different generations of communications where we've come from and kind of to the present where we might be going to set the stage for that as well. I'm just going to ask these. I'm not sure if everybody's seeing these like blue and black lines. I'm not sure where they came from. Should I stop sharing and try to come back in again? Would that possibly erase those so that we don't have those on every slide? Let me see if I can do that for a second here. All right. I'm going to go back to, I'm not seeing him on this screen, so I'm going to go back to share screen, go into my talk again. Oh, okay, good. They went away. All right. So what I have here is just a plot of a frequency spectrum. It's 20 megahertz wide in the plot, and it's showing the magnitude. And it's basically a 2-path channel. There's a main path, and then there's a delayed path. The delay is about 40 nanoseconds, sorry, 400 nanoseconds. And it has a gain that's 95%, basically the main path gain. And what happens, of course, at different frequencies is the delayed path can be out of phase by 180 degrees. Those are the low points here. And when they're aligned in phase. Those are going to be the high points here in the characteristics. So you can see it can be good or bad across this frequency band. And so the history of communications was, well, I didn't put 1G up. It was even more narrow than this, about 15 kilohertz to 50 kilohertz there. But starting with 2G, going back quite a ways, the signals were about 300 kilohertz wide. And okay, if you get unlucky for this simple channel, it could be in one of those notches, and you would have very unreliable communications in that particular situation. So what happened as we went to 3G was wider spectrum. So spread spectrum techniques basically are more robust. And instead of having maybe one dimension every 3 microseconds, think of a dimension as kind of a symbol or a transmission or sample. They became grouped 64 dimensions over a longer time period. They're 500 or so milliseconds. But that wider signal, you see that 1.2 megahertz, with a little bit of coding, you can recover what's lost in the notch. So you've got better communications just because of that robustness. 4G and really Wi-Fi systems in their narrowest channel use about 20 megahertz. Now 4G has different channel widths, but I just showed 20 here. And of course, again, you're getting more robust as you use more dimensions, use a wider spectrum. And so you put a code on top of that, you can do better. And those systems roughly have about 160 dimensions. Typically they're frequency indexed or multi-carrier methods that are used there. And it's about 160 dimensions for every 4 microseconds. So more robustness, getting better, but of course using more of our precious resource spectrum to do that and sharing it in different ways. So as we go from 4G Wi-Fi, a Wi-Fi 5, 6 range into the future, this width here that was 20 megahertz now becomes even a small fraction of the total bandwidth available. Here I'm showing roughly about 400 megahertz, which is the maximum for 5G wide bandwidth, and Wi-Fi 6. And again, more dimensions in the same amount of time, a few microseconds showing up here, the 2G, 4G, 5G, all that. More dimensions, more frequency used, potential for better or more robust transmission system. And we not only can add dimensions in frequency, if you will, by widening the bandwidth, but starting around 4G, we also had space-time or time-space systems, MIMO systems with multiple antennas. Here I show 8 transmit and 8 receive. They're in the diagram. And if those are spaced roughly a quarter of a wavelength or more apart, they essentially become independent. And the noise that is at the receivers is independent. And so you get more dimensions, more ability to look at signals and become more robust or improve data rates, improve speeds, or the number of users that can use the system. So the number of channels that you can create can be up to the number of antennas, or these are the so-called spatial streams. And so that adds maybe 2 to 4 antennas we saw in the earlier Wi-Fi and cellular systems, going up to 8 to 32 antennas in 5G, and we even see 6G going wider bandwidths yet. They're talking about frequencies above 100 gigahertz, where that is possible, the terahertz band. Wi-Fi 7, maybe thousands of dimensions per microsecond. So we see this kind of trend to try to use up space and frequency with our transmission systems as we go from the earliest generations to the latest generations. And even I've even seen discussions by as many for having as many as 4,000 antennas in the so-called 6th generation systems. Now, what's important here is that the increase in dimensionality, N I tend to think of as a frequency or temporal parameter, space-time, and then L as a temporal as a spectral time parameter, and then L as a number of antennas, if you will. And so the trend has been use more dimensions, improve the system. Now, how that works, and I've chosen cellular here as an example. You may be familiar with this. Both the 4th generation and the 5th generation systems use what are called slots. And in these slots, they have a number of frequencies. You can think of those as vertically indexed here. And then time. There are several little symbols, if you will, or code words within a time slot. And they multiplex the users onto these systems. Typically, the smallest unit is 12 frequencies on parallel, and then for a single user, then they might have another 12 frequencies, another user, and then those, of course, can be time indexed as well. So this is the temporal system. But in these systems, for cellular at least, they don't overlap. So there's a scheduler there, frequency is allocated or time is allocated. Never the twain shall meet, so to speak, is often the description of that. And those are called resource blocks that are assigned. And then, of course, if you have spatial streams, you can do that also across space. So the scheduler can say, okay, this time, this frequency for this user on this spatial stream, when there are multiple spatial streams created because there are multiple antennas. And so, of course, that can proliferate and allow a certain assignment of users to time, frequency, and space. Okay. And the cellular systems attempt no overlap, and I'm just going to call that OMA here, orthogonal multiple access. And Wi-Fi uses a collision detection system. I'm going to talk about another slide item, but it still is really even less efficient type of orthogonal multiple access, because you transmit at different times. Simply because there's a collision, everyone backs off in a random time period and tries again. So they're not simultaneously transmitting on the same frequency and in the same space in these types of systems. So those are within the transmission system itself, the cell or the cellular or the access point, single access point, if you will, for Wi-Fi. But there's another level of this orthogonal multiple access that's occurring by regulator. So there are certain frequencies assigned, and I picked the ones here from the United States, but it could really be any country in the world that may be different. But there are certain frequencies assigned for 3G, 4G Wi-Fi here squeezed in 2.4 gigahertz, and then the 5 to 7 gigahertz bands, and then different carriers here on the regulated spectrum, the licensed spectrum, own different swaths of frequency. And if you look across the bandwidths that are largely used, it's maybe as much as about 4 gigahertz I've shown here. There are more carrier frequencies being allocated in time. But a reasonable assumption is that maybe 6 bits per hertz could be transmitted by these systems. So maybe 24 gigabits per second is the total bandwidth that at any point in space, you could all think of it through your bodies, wherever you are right now. It's probably about 24 gigabits going through you, but it's allocated to all these different things. So, that's kind of static in terms of what's done. And you start to ask yourself, is that really a good thing? Because is all of that bandwidth, for these different groups, competing in stationary allocated being best used in this way? Or are there ways to share that or redistribute it dynamically? And of course, the regulator is the one who assigned these fixed spectrum bands. And so you start to see the theme emerging for the talk here today is, suppose this becomes a lot more dynamic. What would happen? And if we look at unlicensed, you can say, well, that's kind of doing that. But yes, it's a collision protocol. Now there are some scheduling things that have been added in Wi-Fi 6 that some of you may be familiar with, which try to make it a little closer to cellular. But nonetheless, even the cellular systems still have this orthogonal multiple access where everyone really gets their own slots in the system. Is this really close to doing the best possible? And I'll mention as well, kind of a step in the direction of the artificially intelligent regulator, if you will, is Wi-Fi's latest automatic frequency control, which basically the Wi-Fi system itself, the access point can go to a database. There are a few companies that have a web service where you can send in your IP address there and you get permission to use some of the frequencies of the new 6 gigahertz band at maximum power if you get a yes back from the system. And that is kind of the regulator really starting to have a policy that is at least geographically dependent. So it's slightly dynamic. These systems, as I understand, are pretty stationary today. They're not, there's updated infrequently, if you will, in terms of what's allowed and what isn't allowed. But it is a kind of first tiny step towards a little more dynamic type of handling of all this spectrum and space that we have. So, and you could look at this as kind of a very slow collision protocol, if you will, over space. So having that said, let's look at what's happening on traffic. So this credit to my company. I worked with a group called the Dynamic Spectrum Alliance, which is a number of internet companies, kind of a lobbying group for spectrum. And we collect a lot of data on Wi-Fi around the world. This is kind of tens of millions to hundreds of millions of Wi-Fi devices, customers that are collected. And so we kind of get the distributions of what's going on. And you can see here the growth in the number of gigabytes per day that the Wi-Fi systems are using in Europe. There's kind of a steady growth in both the 2.4 and 5 gigahertz band. It's doubling about every 3 years in both of those bands. You'd see similar trends in the United States. For that, there are some graphs in a report that was released, but it's slightly ahead. It's running about 9 to 12 months ahead of Europe in terms of the volumes and uses and problems associated with that, but pretty similar growth trends, just a delay really on that. And here's another kind of interesting plot here on the right. What percentage of the time is the bandwidth being limited by the Wi-Fi? And you can see that that's going up with time. There are two things there: more people using Wi-Fi, and then of course the bandwidth of the access links. As more fiber goes into networks, that goes up. So there's an increasing probability that your Wi-Fi speed or your access, your wireless speed is limiting. And I submit if that is happening 10% of the time or more, that could be a problem. Indeed, you could have a lot of angry users who are not getting the full bandwidth that they thought they got from their internet service because they're being limited by the wireless connectivity at the end of the service. And you can see it's really bad already in the 2.4 gigahertz band in the United States, and then the 5 gigahertz. It's already bad and getting worse. Of course, the 6 gigahertz band has recently been allocated. I don't have any data on that, but presumably it's much lower here, and that was a good thing that helped. But certainly things saturating. Give you a little bit more indication here, a little more detail. Downlink, uplink, if you will, Wi-Fi data, interference, which is other access points and how often are they disrupting you. Congestion is traffic in the busy hour with all the devices that are using the same access point. That grew a lot recently. Latency going up, so forth. And Europe, you can see the trends here, but not the 2.4 gigahertz band is still, as I mentioned earlier, but it's run about a year or so behind the US, and that you still see the 2.4 gigahertz having more problems, but as they move to 5 gigahertz, that'll go away. We tried to come up with a single score by kind of combining in a simple way some of these critical parameters and aggregating them, if you will, and give an idea on spectrum need and how fast is that growing per year. And you see the North American, the 37, the 5 gigahertz is getting used more often. And so the 2.4 is actually being less occupied, still full, but traffic shifting, whereas that's still underway in Europe. So spectrum need rising about 25% a year is what the conclusion is across this pretty large set of data. So obviously more spectrum helps, but a lot more use going on the aggregate data, which is more users and more data per user happening. Now we can say, okay, well, we've allocated more spectrum, so that's good. But basic electromagnetics, the loss, this is in free space, increases. So in other words, the degrades with the square of the carrier frequency. So spectrum up at 60 gigahertz relative to 6 gigahertz is about 100 times less power efficient. And in fact, this is an ideal number. Typically that exponent on the f sub c squared there is more like 3 or 4. It can be as bad as 5, depending on the environment. So the signals don't travel so as far with spectrum. So it's going to kind of force more efficiency. It is possible to use lots of antennas to try to improve that, but it's not enough to overcome completely this increase in attenuation with the higher frequencies. So what is needed is more cell sites or access points closer, which means more wires and fiber to get those towers or access points closer, and that costs a lot of money. So it's going to become, it is already, and it's going to become increasingly costly to outnumber the users, which is going up rapidly. We talked about tens of billions to $1 trillion earlier with antennas. At some point, that's just not going to be possible anymore, even if the antennas are getting smaller. So we've heard of the Heisenberg uncertainty principle. It says the wideband's more certainty principle, which is wider bandwidth tends to slow time's appearance. You get more samples in a given unit of time, as long as the communicating devices' speeds have the same limits, like maybe walking or driving speed, or just sitting or standing still. We have that, and so we get more looks at it in a given time interval. It's actually possible to learn more, which is helpful to artificial intelligence. So if you have a fixed coherence time, you get more looks. And that means it looks increasingly stationary at wider and wider bandwidths. So you can estimate the channel more accurately, and then you can exploit that. And in fact, the systems are doing that today. So, and you can spread the power you transmit over more bandwidth. Of course, you need the more bandwidth to do that. That's a fundamental in communications. Some of you may recognize this formula. Here is the Shannon capacity formula, where you have the bit rate that you can send is limited additive white Gaussian noise channel by basically the log of the signal to noise ratio. But if you spread your power P over n times more bandwidth, the signal to noise ratio goes down, but you had n times more bandwidth, and this is linear, that's logarithmic. So that's a spread spectrum effect. It's always, if you have the bandwidth, it's always better to use it from a fundamental standpoint. Somebody gives you double the power, double the bandwidth, always take double the bandwidth if you can get it, because you'll get a better improvement in your system. So that's going on, and someone might say, well, that's for a nice clean channel. What if you have multipath or intersimilar interference? It still basically applies. It's going to be the widest. If you know what water filling is, it's a technique to decide what frequencies you should use and which ones you should zero, but you're just going to do that over a wider interval and find the places where the transmission channel is best and use those. But what about crosstalk? Okay, from all the different users. Okay, this is for a single user, this formula here. Obviously, if you're going to allow some things to overlap in time, frequency, and space, and you're going to optimize over that, one of the possible choices is to prevent them from overlapping that you would consider in optimizing. But there are other choices as well. And so it's going to be at least as good. And you start thinking about, okay, how much better can it be? So let's try to go there. And to help us, we're going to need to become smarter, and we're going to need possibly much more computational power. So you may be familiar with some people call this CIPRI or eCIPRI, formerly X-Hall, split 7.2. The basic idea is you have at the edge of the networks more and more computing power, and you could put artificial intelligence in the cloud or at the edge. And this 7.2 basically allows you to do all the signal processing, modulation, coding, as well as the higher level functions, basically here at the data center. And essentially what's left out here at the point where you go wireless is just A to D converters and DACs and maybe an RF tuner circuit to take you to the right carrier frequency, and you go to the devices. So a lot more software power, and the architectures are evolving to allow it to be used for signal processing purposes. So edge and cloud computing advances, tens of teraflops there. And then intelligent regulation, if you have this computing power, let's say for maybe 100 megahertz wide channel, the amount of compute power that you need to handle an individual one of those is maybe a few hundred mega operations per second. So computational power is going to be there to possibly do this. So just a shout out, one of the companies I'm associated with, former student, the founder started this. They have a technique for fiber or copper systems where they basically take advantage of this, and they have a little, it's actually kind of an analog modulated signal at IF. It rides on the wires, and then when it gets to the endpoint, then it goes wireless at that point, and the channel is the cascade of the wired and wireless, and that helps set up these types of opportunities. More generally, this split 7.2 has other forms as well, but it puts the phi layer signal processing and modulation over here at the edge, as I show in the diagram, and that would help artificially intelligent regulation, if you will, be able to do more sophisticated things. And I've got a little website here and a paper that was published on that. So with that kind of sets it up. So what are the tools that we have available to us as communication engineers to be able to address these challenges and evaluate them and say, how well are we doing, and could we do better? And if we could, how might we do that? How costly would it be to do that? So multi-user communications, we have a transmitter and receiver for each of the users in a system, and they're sharing some type of resource. So we could have a mobile system on the left, or we could have an access system or an in-home system, as I try to show, or inside the business system on the right. Downlink or downstream, it's a one-to-many type problem, sometimes called a broadcast problem. And the uplink or upstream is a many-to-one problem, often called multiple access. Those signals might be relayed from one place to another, sometimes called a mesh network. And you can have overlapping combinations of these things, which is sometimes called interference channels. More formally, take it back, and sometimes we almost forget our fundamentals in communication sometimes, but they're nicely expressed in terms of probability distributions. And if you have an input to a channel X and an output Y, there's a joint distribution for those two random variables, the input being the signal that represents the messages sent, and the output being what was received at the other side. And the channel, in its most general form, is characterized by this conditional probability distribution, the probability to get a certain received signal given an input to the channel. And we can have a transmitter with a message. It creates a certain distribution of messages. Usually that's uniform, doesn't have to be. And there's a receiver, and we basically try to pick the estimated message such that it essentially maximizes the probability of being correct or minimizes the probability of error. Now, that doesn't really change for multi-user systems. You might have a bigger conditional probability distribution of output given input for the channel, but it's still characterized in the same way. And you can see I put a little index of 1 and 2 here for the two users in the system. You can think of the two users together as X, they're components of it for each user. And then same thing for the received signals, Y. And what always assume here in multi-user systems is that the messages themselves are independent. They're coming from different places. And so that probability distribution factors. Now, if you happen to co-locate the transmitters, like that downlink problem we were talking about, cell tower, access point, think towards all the communicating users or devices, that's called formally a broadcast multi-user channel. And if you co-locate only at the receive side, but you don't have co-location at the transmit side, kind of the dual of the broadcast channel, it's called multiple access, kind of many to one. And there is a maximum reliably decodable. That means you can make the probability of missing essentially as small as you like. But because we have more than one user, it's a little more complicated than just a single formula that characterizes what the best or highest transmission rate could be. You get a region because you have two users and one has maybe a number of bits that it carries per dimension or symbol and a rate that's associated, the number of bits per symbol per unit time. And you plot them jointly and they may not be independent. If they were independent, it'd be a nice box here. And you wouldn't care. That's what the OMA systems try to do, is create a box for this. But there's a trade-off. One user gets a lot of data rate, the other one may not get so much data rate, like this point over here, or that point over here. There may be other points where it's a little more equally balanced between them. That's called a capacity region. And it's a function of the two users' data rates. And it's kind of easy to plot in 2 dimensions. So you see this here, but you can imagine with many more users, it's a more complicated surface that you get, but nonetheless, fundamentally, there's rate pairs or rate vectors for the users that you can achieve, and there's more than one of them. And so there's a trade-off in terms of how fast you can go on with one relative to the other. So if you look at the basic multi-user channel types, the downlink I mentioned more formally may have a number of users. I like to call that capital U. There's a single encoder that somehow gets all those messages together, launches a signal into this broadcast channel, characterized by a probability, conditional probability distribution, and the receivers are in different places. So you got detectors in all these places. But nonetheless, communications channel, same form as you saw earlier. And we can have the opposite of that, the opposite direction, where the transmitters they're in different places, so they can't coordinate. Nonetheless, the receiver is in a single place. It sees all those messages. That's called the multiple access channel, or MAC, if you will. And then there's the situation where both the transmitters and the receivers are in different places. You could kind of think of this as maybe roaming from one cell to another, or other situations where you can't coordinate on either side. That's called the interference channel. And then finally, if there's some relays that are involved, you may be retransmitting the message from some intermediate points to try to get to the endpoints, again, capital U users. So these are the 4 basic types of multi-user channels. And I submit to you that, at least I'm not aware of it, these 4 cover it. Any multi-user communications channel can be broken down into one of these 4 or combinations thereof. And I like to call the combinations nesting. And here I have an example of that might resonate with you all. You have Wi-Fi, you're at home, you may be using it now, and your neighbor's SSIDs are visualized. So there's some overlap. They compete for spectrum with you. And so what happens is inside each of these homes, you have a broadcast channel from the access point, if you will, to the devices, downlink, and you have a multiple access channel uplink to the access point. But then you have these shaded big circles. You think of those as kind of macro users, if you will, and they are interfering with one another. So that's an interference channel, which is comprised of these little broadcast channels and multiple access channels. So you have a set of these macro users in the system. And if there were relays and measurement points, you kind of get the idea. Those are the 4 basic types. Okay, things are going to fall into those categories, and you can kind of nest the problems. So you can solve them at a lower level, and you get a certain resource use at that, and then you can solve it again at a higher level and look at how well that you can do. So that's multi-user kind of communication theory summarized, if you will, in terms of these component types of problems. And important increasingly, and I like to go back and quote, if you read the first few lines in Genesis in the Bible, what did God say? I think everybody gets this, is let there be, and I've added Gaussian light. So for electrical engineers, we can all be very proud that we're studying the first thing that God did in creation, electromagnetic waves. That's our specialty. But when there's a lot of them through the central limit theorem, a lot of random things adding together, including light, tends towards a Gaussian distribution. So we have a lot of crosstalk, a lot of users, and they're interfering with different systems. They tend to be Gaussian. And we also know that good codes for single user channels, when you have Gaussian noise, are also Gaussian or close to Gaussian in terms of the transmitter distribution. So everything's kind of Gaussian. And it turns out that those single user codes are fundamentally that they're all you need. You don't need to have special codes for multi-user. You can use those same codes. You can play with other parts of the system and get yourself basically to the best performance that way. So essentially, we have these basic multi-user problems that everything with good codes and lots of interference and so forth is tending towards Gaussian. And that actually makes it a little easier to solve some of the problems. So I'd like to take that another step further here. We have a Gaussian channel here I like to call the matrix additive white Gaussian noise channel that is linear in terms of the X, the transmit signal, might be many users here. Yeah, there's some H here that basically represents any kind of distortion effects that could be temporal, so intersymbol interference, or it could be crosstalk between the users. Add noise to it, Gaussian noise, get an output Y. There may be so many dimensions, think antennas here. There may be so many dimensions on the output, think antennas also, and you get this model, Y equal HX time plus N. And pretty much all the cellular systems today and Wi-Fi systems and wireless systems and wireline systems tend to use this model and or pretty close to it in most forms. And there are techniques for handling this channel. And essentially, I've got the names here, a variety of different names for different situations, space, time, exactly how you do it. But the basic idea is to decompose it into a parallel set of independent channels. So they get these nice little channels that are really free of one another and have a certain signal to noise ratio. That noise might include some of the other users' signals. And so you do that for any system and try to decompose it this way into a set of parallel channels. Now, what we see in wireless increasingly is that they do this in frequency, and there's a frequency index that is occurring. So we kind of have a modulator for each tone, if you will, of the system. But then we also have multiple antennas. So I like to think of the transmit side L sub X. So there's basically a transmission system that does an inverse Fourier transform for each one of the antennas. That goes up into space over the channel. And then on the receive side, it comes back down through the reverse of that. So we go into the frequency domain, but there's one for each of these antennas. And the transmission systems basically try to separate it into a frequency problem and then to use the multiple antennas on each and every one of the tones. And if it's all synchronized, you can separate the signals that way, but you still have to deal with the users who are all sharing the same frequency and time on the same antennas, if you will, or same set of antennas. So it's not necessarily equal energy everywhere, but you can optimize that resource that are used. So that starts to sound pretty complicated, but then I remind you of the X Hall or the split 7.2, which is increasingly taking all the signal processing that used to be in the classical systems all out at the radio tower or in the access point, and this DU system is moving back towards the edge of the network. So more and more signal processing can be done there, which allows a greater degree of capability, if you will. So radio units are largely just becoming DACs, A to Ds, and driver circuits. And then this distribution unit has the layers 1 and 2 to signal processing, coding, link layer. And then there are higher layer functions also in those other boxes there. But that was largely in software earlier already, but now you see all the way down to this level. So bare metal switches, which used to be level 3 and above, now going down to layer 1 with this X-Hall capability. And so this does allow the possibility of machine learning or AI to be used in these systems. So let's take a look at that. I've mentioned some of the things here, but I'll get back to them shortly here in subsequent slides. So there's a couple of use cases, if you will. There's the fixed wireless case where we try to go wireless to a lot of homes or buildings. And we have many, many users that way, downlink and uplink, if you will, broadcast and multiple access, I mentioned earlier. And the number of users, kind of the number of served homes. Antennas help a lot if you have lots of antennas here, but you may have a lot more users than you have homes. And then the multiple antenna thing only works so well if you have things that are co-radial. You lose most of the advantage that way. And then we have the in-home as well. And if you can get inside the home, maybe you get on a wire there, or maybe you don't, you have all the devices. So again, lots of devices inside the home, and that's likely going to exceed, it already does exceed, the number of antennas on the access point. And again, you can have the co-radial devices, and they're kind of like undoes some of the MIMO when that happens. So what are the best designs? And I'm thinking more like this distribution unit that you can do. So it turns out that when you study this area, there's so-called canonical processing. Later, it came to be known as NOMA, non-orthogonal multiple access. I use them both here, those terms. Each of those tones in those multi-carrier systems for Wi-Fi and cellular today, like a downlink transmitter, has 3 basic operations down at the physical layer. This is in addition to any encoder decoder for some well-known single user code that's also used for all of the users there individually. And I show them here in the 3 colors. There's a series of rotations. They can be implemented by 2x2 rotations, very simple individual operations. There may be a lot of them. Scalar multiplies. And then there's this red box here that nobody's doing yet, but it's called the triangular or lossless precoder in downstream direction. And the reason they don't implement it is it's kind of complicated. It has some numerical issues with it. It kind of makes the design need to be more sophisticated to do it. And for the uplink problem, basically the box is reverse in direction, but you still have the same basic operations. The channel may be different, but the constituent values inside these boxes may be different, but the basics of the operations remain the same. And essentially they come from what's called QR factorization of that H matrix that characterizes the channel. The series of rotations needs to be learned, the scalars need to be learned, and the triangular off diagonal components would need to be learned. And they also, I'll mention that those red boxes are nonlinear, but there's a theory on this. And these systems can be nested, and then the same basic operations apply to that nested system also. And then you can combine good single user codes like polar codes or LDPC codes or others. You don't lose anything by using those on the multi-user channels. And basically you can get to the best possible performance. So if we could implement this accurately at high speed, what will we do? Well, this G thing is kind of important in certain situations. Without it, and this is the present systems don't use it, you're restricted to the orthogonal multiple access. Every user's got to get their own time, space, frequency slot. You can't have them overlap. If they overlap, they basically knock each other out. And you have to transmit again later. Good news is it's all linear processing, tends to make it a little simpler. Unfortunately, it does increase the delay in scheduling, and it reduces the data rates when you leave this out. No G, basically that capacity region I was talking about earlier, is essentially an orthotope, if you will, a rectangle in 2 dimensions. Orthotope is just a rectangle in many, many dimensions, or hyperrectangle. And it sits inside your region. So the question is, how big are these gaps here? How much do you lose by forcing yourself to this system fundamentally? And can you compute that and figure out the differences? And of course, it's going to depend on the channel H as to how big those gaps are. And what we're going to see is that this grows as the number of users exceeds the number of antennas. So that's why I made a big deal about that at the beginning of the talk. And so here's an example here. It's kind of a simple example, but what I have is 3 users, and you can kind of see the channels here. This is a frequency plot, and one of the users is the blue line, and that's kind of got a notch in the middle, and the other is the red line, which has a little notch, but kind of more band pass, and then the other one is more low pass in its nature. So 3 different channels using a little bit different parts of the spectrum for system, 2 antennas, and then the FFT size I plotted here on the vertical axis is up to 32. For this particular channel, you don't need a huge FFT to get good performance that way. And what I did was I put the non-orthogonal optimum up here. So this is the best you can do on this channel. It's the sum of the user data rates, because I got 3 users, I plotted the sum. And then with only 2 antennas, the number of users exceeds, and you can see it drops off here. That linear system, that OMA, is maybe 90% or so, the data rate. As you start to increase the number of users, it gets bigger and bigger. This line drops and that gap gets bigger. And so this is the amount that we're losing as if we don't do the optimum processing, and that becomes pronounced when the number of users exceeds the number of antennas. And you can actually get into this and start characterizing it. For this effect to be negligible, the number of users has to be less than the number of antennas, which turns out to be maximally the rank of the channel matrix H, so the number of independent rows or columns. So you can typically get 1 dimension per user, and we call those the primary users of the channel. It's very similar to what the government or the regulator calls the primary users. Those are the ones that have first rights. And the secondary users are all the rest of the users. And they're going to need to freeload, if you will, or share the primary dimensions of the channel. And this is where the sharing could be delay or wait a lot of time, but if you get too many users, you start to lose quite a bit as you do that. And if the number of users exceeds the number of antennas, the best thing to do is not necessarily delay or try to wait for everybody to have their chance. You have too many users for that. So you need to start sharing. And you use those structures that I put up previously. And as these secondary users, and you can figure it out for any channel, which ones are the secondary, it depends on the channel. As you start to energize them, they're not quite as good, but they need to use the channel. So everybody's data rate comes down a bit, and particularly the primary users, but all of the rate sum also decreases, as we saw. And so you get into these trade-offs of how well can you do. So if you use the nonlinear systems, what's the difference? And I'm estimating that value that you saw earlier. What are its limits? I'm calling it M air here. So we saw bandwidth increasing from 2G to 6G systems. The N goes up, the L goes up. But there's another factor here that relates to this rate sum and how much of it is secondary users. And that's going to depend on the channel and the needs of the users, and how much of it is the primary users. You get the best rate sum when all of the users are primary, but that's not necessarily guaranteed. So as that secondary set of users start to use more and more of the available bandwidth, you can get them in there and you can share them. And the advantage that you're going to have over the systems from today, it theoretically can go to infinity here, but more typically, it's going to be a nice factor if we got a lot of users, because there's going to be a lot of secondary users and they're going to need to use the channel. So we have another kind of thing we can exploit that we're not yet exploiting in wireless systems. If you look at the computational load for this, I'll kind of go quickly here, but with 4 antennas and 16 antennas, and then the FFT size is 64 to 1024, you can see here anywhere from hundreds of mega ops to giga ops in a system. And this system split 7.2 XHAL, of course, allows that computational power to be at the edge. And those are implementable numbers at that point, but that's not the complete story here. Those are basically the signal processing and modulation level. But the policy, the decision on which user is more important, what point do you pick in that rate region, and how do things work for it, that turns out to be an NP hard problem, okay? It goes up exponentially with the number of users, and the thing inside there that's going up is U factorial. So this gets to be a big number very quickly to try to solve these problems in the exhaustive best case. Now, it turns out if you just have a simple multiple access or broadcast channel, you can simplify that factor pretty significantly. And for the simple interference channel, you can also simplify it, but it's still going to be a pretty big number. And if you start nesting the systems, which is the practical situation, it starts to go back up again. So you don't need to do it every symbol. This can be a policy imposition. But if you start to do things for reasonable number of users and reasonable time intervals, you may get into the teraflop area's basic conclusion here, but that kind of computation is potentially available at the edge. And then I just make a few comments here as we're about an hour into this. I have a few more slides that I'll try to go quickly, but distributed antenna systems basically would be an example of one of these multi-user systems. We have a management interface between some kind of, I call LRM, Learned Resource Manager, and the radio node, Wi-Fi, LTE, 456 generation cellular. And we start getting overlapping nodes, and there's a manager which has policy and maybe another one, and it has a policy provided to it where the artificial intelligence is there. And we start to try to approximate with artificial intelligence, those algorithms I was talking about that they're now known on how to get the best optimums for multi-users. And then how do we trade off? How do we pick a point in the rate region? It's going to depend on the quality of experience of the end users. So those are things that the policy, if it starts to become more dynamic, this concept of an artificially intelligent regulator could help significantly. So most machine learning is complicated. You don't really need it for the physical layer stuff that's at the edge in terms of those matrices G and Q and S that I was talking about earlier. Those are fairly simple and can be implemented, but the exact users who are most important, the spectra they use, the energy levels they use, that's where you get into the NP hard problems to solve. But nonetheless, we know that those types of problems are often well approximated and solved by machine learning systems, deep learning systems. Here I showed a neural net, but basically the idea is using those types of techniques to decide which users in this situation are primary and secondary, under what conditions or policy, are they one more important than the other? What kind of energy and spectral levels should be used when you see certain conditions at the edge? What's the best thing to do? It becomes dynamic and artificially intelligent. So that's the concept there. And then again, reminding on the XHAL, the complex software, this machine learning could be done at the edge or in the cloud or combination. And that's happening through virtualization today. Bare metal going down deeper, really getting truly bare metal. And so we begin to use these techniques increasingly to try to get this last or area gain that we've identified beyond just spreading the spectrum and using more antennas, because we're not going to be able to outnumber the number of users eventually with that. And if we're going to do it that way, we may want to use indications back from the applications, as long as it's machine learned or artificially intelligent. It doesn't have to be just a packet error rate anymore. It can be a quality of experience concept, which we can machine learn and then use that to pick the points in the rate region and then drive that through the algorithms to hopefully a successful or better use of wireless spectrum. And if you have a system like that, once you've learned the channel, you can also adjust. That's basically the policy imposition. Maybe some simple examples of this, just to give you an idea, kind of a state transition diagram in terms of policy. Certain conditions, you might be in one state of this system, and maybe that's good. Maybe best state has got highest data rates, and you might be in a bad state, which is really bad performance or quality of experience. And so the policy says, okay, take some measurements locally, implement this policy here, and you can figure out the answers to that at the edge. And the idea is to try to get to the better states. And these are often called Markov models or state machine models. And you can figure out certain stationary distributions that are good for them. And so that becomes a way to basically implement the policy so that you're not doing that every time locally, but you're imposing a policy to the different nodes. And then we begin to use all those different frequencies that are available. Instead of assigning one to each of the operators, as we talked about earlier, or allocating everybody their own spot, but we begin to share and use artificial intelligence more. So how can spectrum policy become more adaptive and dynamically mapped to each situation? What's the value? We talked a lot, it could be a large value, at least in terms of fundamentals. What's fair or neutral when you do that? It's always a question with any kind of allocation of resources or spectrum. Which point in the capacity region do we want? And what are the challenges? Well, basically create an implementable adaptive policy that dynamically handles these resources along the lines that we talked about. And we know that the NOMA is kind of a superset and can be significantly better. And then use the right types of computing architectures, machine learned or otherwise, to try to handle that. So in conclusion, the gains still could be large. The present systems are good up to a point, but once that number of users starts to exceed the number of antennas, it's not so good anymore. Actual computational complexity could be doable in these systems. And then, of course, training them for learned quality of experience, as long as we're going to an AI type system, would be good. Hopefully the robots won't replace us engineers yet at Array, but they might just have a chance at helping the regulators to do a more dynamic job in the future, and we get away from that fixed spectrum allocation where everybody's got so much data rate going through their bodies, but they can't really have access to it because of these static rules that we've imposed. So that's my conclusion here. I thank everybody for your time, and happy to answer questions at this point.
Okay, thank you. And if you have questions, you can unmute yourself and ask questions, or you can type in the chat room your questions. And before you leave, please finish attendee survey.
So I think I'm seeing some in the chat box. I'm looking over there now. This one from Sharif. What are the challenges for AI computing at the edge? I think there's a couple that you see, or I tried to identify in the talk, which is that those three basic operations themselves could be synthesized in GPUs, kind of the special purpose processors that are increasingly used for for tasks along with a central processor, obviously, that's dividing the task and then hitting them to. So those, I think, could be done with GPUs, and they tend to be things that are going to be of two types: 2x2 rotations, lots of combinations of them across space, frequency, and time, and then also the triangular operation, a nonlinear operation, which is actually a back substitution algorithm in mathematics for that. And then there's those AI problems, which are more challenging, but they tend to parallel basically convex optimization problems or combinations of those types of problems to solve the various multi-user situations. They don't have to be solved every millisecond at that level, but they do have to have some kind of regular solution that updates with the environment as it changes. So I think those are the two main challenges: that edge computing platform that does the AI, and then the GPUs that are going to be implementing those basic operations.
Do you have any comments about doing that AI work in analog rather than digital electronics?
I haven't given much thought to it, but if it works, it works. It'd be good for the basic problems. So I think so.
And also applying this kind of thing in millimeter wave and sort of unlicensed bands.
Well, I think the unlicensed or the licensed, it's the same thing. You have a resource management that you're going to do. If you know that it's unlicensed and there's possibility of collision, you may manage the things that you can't control a little bit different and basically try to avoid them if you can, but still share on the things that you can control in a better way for that. And it was the second part of your question. Sorry, I think I forgot it.
It's just applying things in millimeter wave.
Oh, yes.
And free space optics and other areas.
Well, obviously, as the bandwidths go up, the real-time signal processing gets it gets more intense just because you're running faster on everything. But as far as I have seen on that, I'm not outside of limitations on A to D converters and D to A converters, so forth. Mm-hmm. The basic linearity and Gaussian things and that still hold true at those levels. And of course, the antennas, to get lots of antennas, they're spaced more closely, so you can do that physically a little bit better. Although obviously the RF, the higher up you go, the more challenging the circuit design is to have that be clean. I think I see here, how often would the AI need to teach again as the network changes? Well, there's a couple of things that you need to look at there. One is the actual kind of coherence times and so forth, which aren't too bad. Those are, I think they can be handled. They're at kind of the millisecond level, but with codes and robustness used in that, you're probably okay to operate in seconds or even tens of seconds. What you need to do is learn the probability distributions of the likely events, and then have a policy that you impose that then locally, where you have less computation required, you just implement according to that policy based on what you've seen. And in fact, the learning then could even go to the level of observing daily trends and so forth for the AI part of it. Once you have a decent policy, because you've learned what we tend to be pretty repetitive as human beings and using things and doing things from the same places and at the same times of day and so forth. So I think that those are the kinds of rate of time changes you would be looking at. As I look at the next question, what would happen to national, e.g. FCC and global IT rate using AR? Well, the tongue in cheek would say they'd be obsolete. And we don't need lawyers, we don't need doctors, we don't need engineers, we don't need regulators anymore. But I think they will play an important role in trying to say not so much which spectrum goes where, but what is the policy that the AI would apply to the situation so that we get a better use of spectrum. It's not going to be static anymore like it has been largely to date, but still, how are those policies imposed? And hopefully it becomes more efficient, more egalitarian for everyone.
Oh, related to that, are there any standards efforts going on right now in this area?
Well, there's plenty of kind of standardization things that have to do with kind of edge management, mobile computing, and so forth, capabilities. The XHAL 7.2 and so forth are standardized as well. As far as the nonlinear thing that could help, somebody has a question about Qualcomm and Broadcom. No, they're not using those nonlinear precoders yet. They are a challenge from an implementation standpoint to do. But as the number of users increases above the number of antennas you can reasonably do, then that advantage goes up. And so it could be quite large, but then the chip providers and implementers more generally would need to, to move to those techniques, which are basically add-ons to what they're doing today, but the add-ons may not be trivial. And I think probably the biggest challenge is when you have these triangular types of things, which you do need to be canonical in these more difficult situations, they're a little bit prone to numerical errors. Whereas the typical operations like FFTs or the MIMO systems, which are just the 2x2 spatial rotations implemented in a 6C, those are pretty numerically, they're very good numerically. They're better to implement, whereas that back substitution process can propagate errors pretty quickly. So there would be issues there that would need to be addressed. But as far as I know, the outside of a long time ago, there was a very simple form of these nonlinear precoders. They call it Tomlinson precoder that showed up in voice point modems a long time ago. And they had all kinds of numerical issues back then. But those techniques have not yet found their way into standards, but they may in the future as the need increases. There was a question about market players or others, your customers for licensing it. I'm not sure what I'm not sure I understand that particular question from Sharif there, Zada. Maybe if you can
Yeah,
explain.
I was just asking, that was a follow-up question to my previous question. If you could quantify your performance improvement that you get from the AA at the edge, and if you have like any, I mean, I don't know if you can disclose your customers, or I mean, who are your customers or licensing your technology?
No, this as I said at the beginning, this AIR is not a product today. It's really just kind of, I've got my Stanford background behind me. This is kind of projecting future directions and what could be the possibilities. And I don't see this as being implemented commercially in the next couple of years, but I think if you look at the telecom industry or generally internet service providers, the change you don't measure in a couple of years in that industry. It's really, it's 10-year intervals. So if we look at today relative to what wireless was like 10 years ago, it has substantially improved. There's a lot more that we can do, but in a 1 to 2 year period, it seems like nothing changes, right? So this is kind of another generational type of thing, but would, just as we went, from narrower spectra to wider spectra, and then to MIMO, well, then the multi-user techniques, we're really just scratching the surface there in terms of the improvements that could be possible.
So probably the first step would be the standards, right? To get it to
Yeah, and of course that process is always
right.
Is always a challenge for all of us who've been through it. I've been to many standards meetings in my lifetime, but if you have really good improvements that you can quantify for this, and we're just beginning to look at that and the different situations, the realistic situations. One of the ones that one of the major US carriers asked me to look at in the Stanford context was just the 28 to 30 gigahertz band, where they're trying to offer millimeter wave fixed wireless access. And how much better could things be if you start using techniques like this in the future? And the current answer is, I don't know, but it may take a few years to do that. But the basic principle is, if you don't have that many users, what they're doing today is pretty close to the best they can do. But as that number of users starts to increase and it gets above the antennas, they get increasingly distant from what the best things to do. So those architectures they're using do not scale to that situation. I don't know that there's a full appreciation of that yet in the industry what that difference might be.
Another follow-up for the edge computing, I don't know, I'm asking too many questions, but you mentioned GPUs. As I was under the impression they would be like more of like ASIC integration with the SoC of the wireless. But I understand it's not like in products yet, it's more of the research.
Yeah, well, I am aware of some companies, the major 3 or 4 semiconductor groups that participate in wireless do have various schemes for edge computing, which is a combination of the traditional CPUs and then GPUs as necessary for certain types of functions that would make the mobile edge computing more efficient. So I think there is some effort to do that. Whether they're using the techniques I'm talking about in this talk completely, no, they're not doing that. But even just for the things that they already have in 5G, for instance, trying to make full use of those capabilities that are there requires GPUs. And so I've seen things from some of the chip manufacturers who believe that's strongly a GPU problem. And then I've seen one from another major chip manufacturer that's more CPU oriented. So even that, I think it will be controversial depending on who it is.
Thank you.
I might have missed something, but I'm not seeing any more questions in the chat box, Priscilla.
There's one last one. Isn't fair to think of AIR as a middle level resource scheduler operating on a much longer time scale of many minutes rather than milliseconds?
Yeah, I think that's fair. I think I like that characterization. Yeah.
Okay, any more questions?
Okay, well, thank you everyone, and thank you Priscilla and Marcelo for the opportunity, and I hope everyone has a good dinner tonight.
Thank you.
Okay, thank you very much.
Bye-bye.